In this video, we're going to talk about why sometimes the noise that we see in the signal chain view for a stage, so for example, this amplifier here, sometimes does not match what we see when we go into the stage view itself, and why that is. So we can see here, we're saying 346 microvolts RMS for this whole stage. And if I go back here, I'm seeing 34.6 microvolts RMS. So this first reason we're not matching is pretty simple. In this view, I've referred to the input, and in this view, I am referred to the output. So if I refer to input, then I will get the same 34.6 in both views. Note that this is referred to the stage input and the stage output, whereas this is referred to the signal chain input and the signal chain output. So if you had multiple stages, it might be, even if you were referred to both of them to the input, you might get a different answer if this was not, say, the first stage in the chain. So watch out for that. Okay, so we are matching right now. I am now, and before we go on, let me show you where this integrated noise is coming from. So we have this noise spectrum, and that integrated noise comes from integrating the area underneath this curve to get that number. Same thing on the stage view. We integrate underneath this curve to get that integrated noise number. So now I'm going to add a filter, which is going to change things up. I'm just going to use a standard 10 kilohertz filter that the tool gives us by default. Now we have a very different spectrum. I'm going to look at our components here. We can see we have this green line, which is the amplifier line, and this is different than we had before. Let me do that again. So there is our green line without that filter. And now if I hop through this quickly, there is our green line after the filter. So you can see that we have gotten rid of a bunch of area underneath the curve, and because we have a logarithmic plot, it's actually way bigger than it seems, because all of this is on the higher frequency area, so there's a lot of energy there. And because we are integrating under a much smaller curve, then our noise total for our amplifier is way smaller than it was before. So now we're getting this 917 nanovolts RMS instead of that 34.6 microvolts RMS. Now let's go into our stage, and our stage is not being filtered, and so we are getting nearly the same thing as we did before. Not quite though. So we're getting 34.5 microvolts RMS instead of 34.6. So why do we have that tiny change? So we're getting that tiny change because even though we're not passing the signal through the filter, that filter is loading our stage a little bit. And because it is loading our stage a little bit, it's going to change our frequency response ever so slightly. Probably can't even tell. And same thing, it's going to change our spectral density plot just a little bit. And so when we integrate this spectral density plot, we're going to get maybe a little bit different than we had before. And we can test that theory. If I hit ignore, then now we're looking at it without the load of that filter. You can see we're at 34.6. If I do use, then we're at 34.5. So that loading is what is making it just a little bit different, but basically it's the same thing. So that's what we have when we have a filter. So now I am going to take off that filter. We're back to our state that we were before with the 34.6. And now I'm going to add an ADC. So let me do 16 bits and 100 kilosamples per second. And that's going to give us this AD4008 ADC. And it's also going to give us a filter that is useful for that ADC. And so just like the filter that we had before, that is going to reduce our noise at the signal chain level. So it's a different filter than we had before, so we're going to get a different number. But you can see that it's still much smaller, this 4.15 microvolts RMS versus our 32.7 microvolts RMS at the stage level, because we are filtering. So that makes sense. So let's look at our spectrum. And here's our spectrum. You can see It's all nice and flat. We can't really see that filter. And then here is our Nyquist where we get this very abrupt cutoff. And so you might think, okay, well, I am going to integrate. I'm not seeing that filter, so I'm just going to integrate from 50 kilohertz down, and I'll get something the same as if I integrate the stage from 50 kilohertz down. So let's just do that for a second. So here I am, my integration range is 100 M to 50 kilohertz. Here I'm going to go make it 100 M to 50 kilohertz. And so we get 1.93 microvolts RMS here at the stage level versus that 4.15 microvolts here, so they do not match. So why, when I'm integrating across the same range and I'm not seeing that filter, why am I getting such a different number? And the reason is that our spectral density plot, our numbers on the spectral density plot are different. So if I look at about 20 kilohertz or so, I see 18.6 nanovolts per hertz for the amplifier. If I go to that same 20 kilohertz on my screen, on my stage screen, I'm getting 8.6 nanovolts per hertz. So why am I more than doubling my noise when I go to the signal chain screen? So that doesn't make sense. What's happening is that I am aliasing. So we have this little checkbox, and I can turn off the aliasing. So the nice thing about a tool is we can do things that aren't actually possible in real life to understand what's going on. So I've turned off the aliasing, and now we can see here is the real noise of that amplifier, and all of this area is actually getting aliased back over here in real life. And so we can see that without that stuff, we're getting the same noise as we get in the stage, 8.6 or so. But as soon as I alias, that jumps up to that 18.6 because all that energy is getting put over here. And so with the integrated noise, I am integrating that 18.6 value across all of here when I am at the stage level versus at the signal chain level, versus at the stage level, I am only integrating that 8.6. So if we had no filter, so that the entirety of all of this noise graph got aliased, then we would get the same answer. Like if I integrated across this entire graph, so I left this setting at 1 gigahertz, and I did this setting at 50 kilohertz, then if I had no filter, these would match. But because I have that filter, they're not going to match. That's just an interesting how the aliasing plays into effect when we are looking at noise. So that's various reasons why when you are looking at noise at the signal chain level, you might not see the same thing that you get at the stage level.